All right, Module 1, Topic A, Review 2 Answers, all possible test questions for Friday. Here are your answers for today's review. Number 1, just skip it. Just kidding. But I did make a note that you don't like bacteria. We are going to answer this question. You may see it tomorrow. Definitely not as complicated. But here's the technique for making it easier to understand. Make a table. X value, Y value. If you make a table and then start to populate that table with some ordered pairs, then it makes getting your x-axis scale and your y-axis scale much easier to do. Although I did hear Jeremiah said that any amount of bacteria over 3,000 and he is out. So I'm going to honor that. I'm going to try to stay under that 3,000 number. Okay, for tomorrow. Anyway, here's our graph. Dave is doing an experiment with a type of bacteria that he assumes divides in half. Dividing in half means doubling. Dividing by a half also is multiplying by 2. Every 30 minutes. Okay, so if he begins at 8 a.m. with 10 bacteria, that is times 0 hours, and he's got 10 bacteria. Every half hour, 30 minutes, he's going to double that. So at 0.5 hours, there's going to be 20 bacteria. At 1 hour, there's going to be 40. 1.5 hours, there'll be 80. 2 hours, 160. 2.5 hours. Let's see, we go till 11 o'clock, right? Yeah. So we need 3 hours worth. At 2.5 hours, we're at 320 bacteria. And after 3 hours, we are at 640. 640. All right? Then, at 11 a.m., which is where we're at 3 hours after 8, at 11 a.m., he decides this is too large of a sample, and he adds chemical A to the dish, which kills half of the bacteria almost immediately. So, also at 3 hours, we're going to have half of 640, which is 320. So, immediately we get down to 320. Obviously, some amount of time would happen. Definitely not hours. Most likely seconds. Maybe even less than a second. But we're going to drop down to 320. He decides that's too big. Okay, almost immediately. The remaining bacteria continue to grow in the same way until noon. So that's 1 hour later. So at 3.5 hours... we double again to 640. We're back up to 640. At 4 hours, which would be 12 o'clock, we're up to 1280. Then at noon, he adds chemical B to observe its effects. After observing the bacteria for 2 more hours, he observes that chemical B seems to have cut the growth rate in half. So instead of doubling every half hour, now it's going to double every 1 hour. So 1 hour later, it is doubled from 1280. So that would be 2560. And then 1 more hour later, 6 hours, is another double. That's 5120. So now we have a table of values, and I can see that on my x-axis, which is going to be time in hours, I'm going to list it from 0 to 6. So I just need 6 to be somewhere down here on the end. Well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, isn't that 25, I believe? So 6 divided by 25 means that I don't know, every fourth line is going to be worth a 1 hour. So 1 hour, 2 hours, 1, 2, 3, 4, there's 3 hours. 1, 2, 3, 4, there's 4 hours. 1, 2, 3, 4, there's 5 hours. 1, 2, 3, 4, there is 6 hours. And my half hours will be halfway in between, so that'll be nice as well. Okay, so we're good on our x-axis. The y-axis is the number of bacteria, and the number of bacteria is my y, and my biggest y value is 5,120, and I believe I have 20 spaces, so 5,120 divided by 20 gives me 256. Every line's worth 256. I'm going to round it up to 300. So my first line is a 300, 600, 900, 1,200, 1,500, 1,800, 2,100, 2,400, 2,700, 3,000, 3,300, 3,600, 3,900, another 300 would be 42, 4,500, 48, 51, 54, 5,700. So I get up there, and all of my data is going to fit on my graph. Feeling good about it. All right, now I just need to plot some points. So at 0, 10, it's going to be hard to see. It's almost on the 0. After a half hour, there are 20. Well, it's also really close to 0. After 1 hour, there are 40, barely above 0 as well. So we're hugging that 0 line of bacteria. After 1.5 hours, there's 80, a little farther up, but not far. After 2 hours, 160. Well, 160 is about halfway between 300 and 0. Oops, I need to move over one. After 2 hours, about halfway up. Okay, getting there. After 2.5 hours, it's 320, so just a little bit above 300. Maybe in there. After 3 hours, it's 640, a little bit above 600, so maybe in there. And then we also have a 3 hours back to 320. So almost instantaneously we go back down to that 320 mark. So far, I'm going to draw this so far. We're hugging the 0, and then we're starting to show the growth. And then he applies chemical A, and we drop back down to that level. So far that's where we're at. Now the bacteria continue to grow at the same pace. After 3.5 hours, we're back to 640, which is that one. And then after 4 hours, we're at 1280. So 4 hours, let's see, 1200, just a little bit above the 1200. So maybe right in there. So here's my graph now, starting to ramp back up. And then we slow it down. After 5 hours, 2560. 5 hours, 2560 is going to be somewhere in there. And after 6 hours, 5120. 6 hours, 5120 is going to be somewhere there, really close to that. And then this is our last movement. Yeah, something like that. All right. So there's our graph of these bacteria. Nothing above 3,000, I believe, was the limit. I'll try to keep that under. It won't be this complicated, but it will make it easier if you make a table of X and Y values so you know what your scales need to be on the X and Y axis. Number 2, decide how to label the vertical axis so that you can graph the data set on the axes below. Graph the data set and draw a curve through the data points. Well, again, I need X value. Well, they've already done that for me, so I've got my X values here. and my y value is on the y-axis, and it needs to get to a negative 64. Well, typically we would like to go down for negatives, but we can flip it around and call the negatives going up, just so that we can graph this. But I do want my 64. My 64 is the biggest number that I'm going to have, and I'm going to divide that by the number of spaces I have available. 1, 2, 3, 4, 5, 6, 7. So 64 divided by 7 gives me a 9.14. So if I count by nines, it'll be not quite big enough. But if I round it up to a 10, those are nice numbers, and everything will fit. So I'm going to make every line worth 10. 10, 20, 30, 40, 50, 60, and 70. And now I can graph those points. So the first point is 0, -1. By the way, these are negatives. Let's make sure that we have that. Again, I'd like that to go down, but since the graph they gave us was up, we can do this. So 0, -1 is going to be really close to 0, somewhere down in there. 1, -2, very close to 0 as well, a little bit higher. 2, -4, not quite halfway to 10. 3, -8, we're getting close to 10. 4, -16, a little bit over halfway between 10 and 20. Next is 5, -32. That's a little bit more than -30, a little bit above that. And then the last one is 6, -64, almost halfway between -60 and -70, something like that. And if we connect, we see that graph looking like that. All right, so there we go, exponential graph. Number 3. Duke starts at the base of a ramp and walks up at a constant rate. His elevation increases 3 feet every second. Just as Duke starts walking up the ramp, Shirley starts at the top of the same 25-foot high ramp and begins walking down the ramp at a constant rate. Her elevation decreases 2 feet every second. Sketch the two graphs on the same set of elevation versus time axes and represent Duke's and Shirley's motions. All right, so I know that my y-axis is going to be elevation. So we're going to start with that. I'm going to put that over here. Elevation, and it is measured in feet. I also know that the highest elevation is going to be 25 feet. So I've got 25 feet and 20 places. So 25 divided by 20 gives me a 1.25. If every line is worth 1.25, then I would get this exactly at 25 feet at the top. So I can do that. Zero's at the bottom. 1.25, 2.5, 3.75, 5. So every fourth line is going to be worth 5. That'll work. 1, 2, 3, 4, 5. That's 10. 1, 2, 3, 4, 5. That's 15. Get in there. 1, 2, 3, 4, 5. That's 20. Did I count it wrong? I didn't fit. Maybe it's. I should have gone every 3. We'll go every 3. Every 3 is 5. 5, 10, 15, 20, 25, 30. Okay, so that'll fit. That'll work. Then we need our time. How long is it going to take to ascend or descend the ramp? Well, if we look at Duke's increases 3 feet every second. So 3 feet every second would take a little over 8 seconds to go up the ramp. Shirley's going down 2 feet every second. That's a little slower. That's going to take about 12 seconds, a little more than 12. So I want at least 12 on my x-axis. So I think I've got 25 there. 12 divided by 25. Every line is going to be worth 0.5 on my x-axis. So that's a 1, 2, 3, 4, 5, 6, 7, 8. Here's a 9, 10, 11, 12. This will be 12.5. That'll be good. All right, so there's my time in seconds and elevation in feet. So we're good. Now let's talk about the two different people. Let's talk about Duke first. Duke starts at the base of the ramp, so he is at elevation 0 at 0 seconds. He increases his elevation 3 feet every second. So after 1 second, he's going to be at 3 feet. After 2 seconds, he'll be at 6 feet, just a little bit over 5. After 3 seconds, he'll be at 9 feet, just a little under 10. So we've got this line here that we can draw. Get a green here for Duke. And that's going to be our line for Duke. All right, next we're going to work on who? Shirley. Shirley starts at the top of the ramp. Well, the top of the ramp was at 25 feet, so that's here at 0 seconds. She's going to lose 2 feet every 1 second. So after 1 second, she's going to be down to 23 feet, somewhere in there. After 2 seconds, she's going to be down 6 feet, so about 24. And 24 is going to be somewhere in that area. Maybe I'm a little off on that one. All right, so as long as I've got 2 points, I can draw the line. And when we draw this line, yeah, it looks like it's going to be right in there. Okay, what are the coordinates of the point of intersection? Well, it looks like we are at 5 seconds. So my x value is a 5. And looks like our y value is a 15. So after 5 seconds and at 15 feet up the ramp, or 10 feet down the ramp if you're Shirley. Okay, and that intersection is the solution to the system. All right, next. The following graph shows the revenue or income a company makes from designer coffee mugs and the total cost, including overhead, maintenance of machines, etc., that the company spends to make the coffee mugs. On the x-axis, we have the units produced and sold. On the y-axis, we have the dollars. All right? How are revenue and total costs related to the number of units of coffee mugs produced? Well, if we look at the number of coffee mugs produced, they intersect, cost and revenue intersect at the point 500 units produced and sold and $6,000. So what does that mean? Well, if we are able to produce and sell 500 coffee mugs, that will equal our cost. Anything before that is a loss, a net loss. We're in the hole. We haven't made any money. Anything after 500 units, and we are making a profit. Okay? What is the meaning of the 0.04,000 on the total cost line? Well, the 0.04,000 is here. That means if we have produced 0 coffee mugs, we have paid, our total cost is $4,000. How could that be true? Well, we probably need a space to produce our coffee mugs. We may need some equipment to produce our coffee mugs. So before we produce any coffee mugs, there are some upfront costs. That's the 4,000. 0 units produced and still a total cost of 4,000 has to be equipment, retail space, startup costs. Okay, last one, part C. What are the coordinates of the intersection point? What's the meaning? Yeah, we already said that. All right. Anything after that intersection is profit. So the total cost is now below our revenue, and that means that any difference here is profit. Okay? Next. Next? There is no next. Study that. Check the videos out if you need a little extra study time. And I'll see you tomorrow for the test. Good luck.